hangover people. People who ate too much, didn't drink enough, and the late ones too. All right, so let me just recall you the definition, since it's an introduction to property T. And also disclaimer, I prepared too much for today, and if I speak really fast, maybe I'm going to cover it, but maybe I shouldn't do that. So I just recall the definition. If this is T is the trivial representation. It's isolated in the dual of irreducible representations. If you don't want to stick to irreducible ones because you like the regular representation a little bit too much, then you should go to all representations. And then there's an equivalent definition that tells you that if the trivial representation is weakly contained in the representation, then it is actually contained. And weakly contained means that there is a place in the Hilbert space where this representation will mimic this trivial representation. So it says that if you can mimic the trivial representation somewhere, you actually have to be it. And the third one is the actual useful definition if you want to prove stuff. It means that you can find a finite set and an epsilon greater than 0 such that each time you have a representation, either it has an invariant vector or at least one element has to move yourself far away from, or at least one element has to move the vector far away. So there is a theorem which I didn't want to prove, but I think it's important to mention it, is if you have a connected simplicial complex and you assume that each vertex belongs to some two faces. I mean, the building will be fine. Suppose that for each x in x, the link in x, the link Lx, the link. So yeah, you probably know what the link is. Take a point and then take a little sphere and look at the combinatorial structure. You get a graph. Well, we got a simplicial complex, but let's take the one skeleton. It's a graph. You want to is connected, and has spectral gap greater than a half. Then any G acting on X geometrically. So geometrically is short for properly co-compactly in bi-isometries. So not a non-uniform lattice in allegro. Uniform lattices, co-compact lattices will be fine. It's going to be a geometric action. Has property T. And so as a corollary, there's two corollaries of this theorem. One, you can read off property T off of a presentation. And another corollary is that SLN-QP and all the lattices have T. And that you could probably go and compute the link with all the stuff you've learned today and compute and plug it in a computer, or have enough courage to actually do it and find that.
Can you be more specific about which spectral gap you're referring to?
Oh, it's the one that Alain Valette.
Yeah, what I mean. So you take the link and then you take what you take.
You take the. It's a graph. It's a one skeleton of the link. Yeah, exactly. The one skeleton of the link.
Okay.
Yeah. The one link. The one skeleton of the link. Okay. And in some sense, it looked like some kind of a converse of Margulis's theorem. Maybe it's not, but Margulis's theorem that I explained yesterday is like you have all those quotients that give you, if you have property T, you get all those quotients. And now if you know property T locally, you can extend it globally. But it's not an if and only if. You can show that for SL and Z, for instance, that's not going to be true. Yeah.
Yeah. Your spectral gap, is it normalized? Do you like divide by the degree when you write 1/2, or is it in the same?
No, you have to normalize it. Yeah, you have to normalize it. Yeah. All right. Okay. Let me just also recall that. Yeah. That's gamma contained in G discrete finite covolume. So for instance, a lattice that can be co-compact or non-co-compact, then G has T if and only if gamma has T. And it is indeed in Alain Valet's book, and it has a non-geodesical proof that I want to say a few words about. So if, for this direction, you use the induced representation, so you assume that the big guy has T. So you take a representation of the smaller guy, induce the representation up, check that if you had an almost invariant vector here, that's really where you need finite volume. You can induce them up, you will find them, the almost invariant vector, you will find them in the big group, find an invariant vector, and it's going to be invariant even more on the small one. And in this direction, the non-geodesical proof in Valette de la Harpe uses that G has, or a group H has T if and only if, so that's for any locally compact second countable group, has what is called FH, which is any isometric action by affine isometries on a Hilbert space as a fixed point. And I like this property. I mean, I like studying property which admits a proper action on a Hilbert space. They're called anti-T because it's a strong converse of, in between admitting a proper action and any action has a fixed point, you can have actions that has large stabilizers but still have unbounded orbits. Right, so this is equivalent to property T, that's actually a result. And for this property is easier seen that if you have something which is finite covolume, so that that doesn't admit any action on a Hilbert space, you induce it up, and that will you get the same fixed point because the finite covolume allows you to average stuff. And right, but and I'm not going to say anything about this this equivalence. One thing which is, I think it's nice and that I should mention, is a remark, is a result by Wang that comments that if H, your Hilbert space, is finite dimensional, then it's relatively easy to say that, to see that any, and G has property T, then it cannot act without a fixed point, and because then an action of G, well, with or without T, is a homomorphism from G to the isometry group, the affine isometry group of H, and this is UN semi-direct product with c to the power n, and that's amenable. Because that's a compact group, semi-direct product, abelian group. And right, so you have your homomorphism, and then you see that the image of alpha, it has to be contained, well, it has to be contained in something amenable, but it's the image of a, if it's the image of a property T group, the image will have property T as well. So the image is finite. And out of the finite image, you're going to get a finite orbit, and then you're going to get your fixed point. Okay. Right. So that's.
There is a small issue with this proof, is that amenability only passes to closed subgroups.
Right. Yeah. I'm assuming. Right. Right. I'm assuming here that G is. That's the argument where G is countable and discrete.
Yeah, but the image could be.
The image.
Dense.
The image could be dense. Yeah, I agree. You have to assume that. You have to assume something on your action. Right. Okay. But this doesn't pass to infinite index. You have to work more to get finite on any Hilbert space. Yeah. All right. So let's go to SL3R. So SL3R. All right. So I'm going to take G is. So that's G. That's going to be G in my talk, and K is SO3R. And inside, I have a subgroup of G, which is the diagonal matrices. And I also have N, which is the set of matrices with ones on the diagonal, something, whatever you want, up, and right? So this is actually a nilpotent group. And there is a decomposition of G as K A K or K A plus K. And that's, how is that called again? Carton decomposition. Yeah, that's called carton decomposition. And then there is also another decomposition, which is KAN. And so we write this decomposition like this, but when you look at the group structure, it's not a direct product. Those guys interact with each other. And it's not at all commutative, but so this is R2, and then it's Rn in general. So that's a nice flat piece. And if you want to think, oh yeah, and right, G mod K is a nice Riemannian manifold, and it's CAD0. So non-positively curved, and but it's and so right, and this one has it's not that easy to understand geometrically. It has this one has dimension 5, which is 9 minus 1 because 3 by 3 matrices, determinant 1, you lose a dimension. So that's 8, and then SO3 has dimension 3 because you have a sphere and then you have the angle. You have two-dimensional sphere and then one-dimensional angle. So when you mod out, you lose it. So it's dimension 5, and so dimension 5 is not that easy to understand. And inside, you're going to find a bunch of flats, and in this decomposition, they're going to be called AK, and then they kind of branch off each other, more or less in the same way that Petra explained that the plots behave in SL3QP, except that there's a fuzz factor, which is there's a fuzz factor. Just the same as a tree resemble the hyperbolic plane. Yeah.
Indira, the diagonal subgroup is not R2.
Yeah, it's dimension 2.
No, you're taking units in R. So it's, well, I mean, it's almost R2, but I mean without the zero.
It's R2 under the exponential map.
It's R2 on the exponential map.
Yeah,
R2 plus.
Yeah, right. I'm thinking of it as R2 plus with the exponential map.
Okay.
Yeah. In fact, it's R2 in R3, where it's R2 with x1 plus x2 plus x3 is equal to 0 that sits in R3. It's a hyperplane in R3 under the exponential. Okay. And so the theorem that I want to discuss today is a theorem is due to Ho and O, except that I read it from Benoit's notes because I could not read Hee Oh's paper. It's too algebraic for me. And it says the following thing is you take, so now, G is SL, it works for SLNR, and K is SONR. You can also replace this by a semisimple group in higher rank. And so, there exists a function which is in COG. So this is a function that decays to 0 at infinity, and it's k by invariant. So it means that that if you do this KGK inverse prime is the same thing as evaluating it on G. It's constant for any G and KK prime, and for any you put the end of the theorem here. So the theorem says that for any pi H, the representation unitary without invariant vector, and for any VW in H, then the coefficients, or rather the coefficients for the unitary for pi, for this unitary representation are bounded by this function time delta V delta W, and I need to tell you, so delta is the function that goes from H to root n union infinity, and that's giving you, it's the k dimensional, so this is the k finite, it's what Shai mentioned, the k finite stuff that he wrote in little. And right, so what is it? It's the root of the dimension which is the square root of the dimension of A times V. And also I want norm one vectors, which okay. So that's question? Yeah.
Sorry, just so this is this function.
This is the Harish-Chandra function.
This is the Harish-Chandra function.
Yeah.
So it is L2 plus epsilon?
I don't know. I think so. Yeah, I think so. Right. So so that's the result, and let's see. Let's see how you get property T from that. Yes.
This function, how is it defined? And isn't it up to multiplicative constant?
Well, there's no unicity.
Yeah, but then you use it to bound something?
There exists a function that will satisfy this.
Okay, that's the...
Yeah. It's you can find other functions. The game is to find the best one. But you can find, yeah. They found one.
It being the same thing.
Yeah, they found one. Somebody else could find another. All right, I'll tell more about this function. First, I'll give you the corollary on how this implies. Right. So you take.
Do you impose n at least 3 only in the corollary or already in theorem?
Yeah, in the theorem. In the theorem. I don't know what happens for SL2. Yeah. Yeah, I don't know what happens for SL2. Okay, so, right, you take your representation and you take, and so it's a representation without invariant vector, and we're going to make a proof by contradiction, which I dislike. I tell my students, you don't give me proofs by contradiction. Lazy people only do proof by contradiction. Just do the direct proof, and if you can't do the direct proof, it means that you haven't understood the argument properly. So that's that's me. Okay. So you take a representation without invariant vector, and take V, which is an epsilon over 2 C almost invariant vector. Okay. So it means that you have pi g v minus v, which is less than epsilon over 2, and you have k c, which is k bi-invariant, and it's a subset. It's a compact subset, which contains C, and which is k bi-invariant. So once you have one, you can just move it around by k, and it's going to become k bi-invariant, and it's still going to be compact if you start with something compact. And so, but you take it large enough, large enough such that there exists G in C with this guy being less than 1/2. So you know that since this is C0, if you go far enough, you're going to be small enough. Right. So you form W, which is the integral of a k of pi kv dk, and this is k invariant. So just notice that if your vector is not k finite, then there's nothing to do, because this is going to be infinity, and we assume that we're in the world where infinity is less than or equal to infinity, and we're done. So we're going to take something which it makes sense to do it for k finite guys. So I'm averaging it, and this is k invariant, and then and I can do it right since v is kind of not very invariant. When I'm averaging it, I get something which is non-zero. It's the same argument then for the compact case. You have something that doesn't move much. When you average it, it's still large enough so that it's nowhere close to zero. So you're going to do v prime, which is w divided by the norm of w. That now this one is k invariant, has norm 1. So this is k invariant, and it's almost invariant. So it means that dv prime is 1. It's k invariant, has dimension 1, and it's still almost invariant, meaning that pi g v prime minus v is less than or equal to epsilon. And then we notice that this, in fact, is 2 minus 2 pi g v prime minus v. And so if you have no invariant vectors, if no invariant vector, then you apply the theorem. Then you apply the theorem, and you get that pi g v prime minus comma v prime is less than or equal to your Chandra function, which is less than 1/2. You find this g, so that's this coefficient. Those are called coefficients for the representation.
Sorry, there is a typo.
Yeah, right.
So, first of all, it's v pi g v prime minus v prime, and then the next line.
Same.
Yeah, and it's
Thank you.
And real part.
And yeah, it's the real part. Somehow I found the real part annoying, so I just dropped it. I think it didn't. Yeah, I pretend that all my vector spaces are real, and cross my fingers so that I don't do anything too stupid. Right. Okay. So you have you apply the theorem, and if this thing is smaller than something, 1 minus this thing is going to be larger than something. So it means that that's pi G V prime minus V prime is going to be larger or equal than a half, and this will contradict this as soon as epsilon is small enough.
I thought you didn't use proof by contradiction.
Sorry?
I thought you didn't use proof by contradiction.
Yeah, I do. All right. So this is an exercise. Direct proof. Right. Yeah. Somehow, but this is a true thing. I think that if you write a paper, which I'm not doing right now, somebody else wrote this paper. You should try to find a direct proof, because direct proofs usually have constructive arguments. And anyway, if you have a result, you should try to find several proofs of your result to make sure you understand your argument. All right, I'm going to try and give you some explanation and proof of this theorem. So while I erase, I listened to a podcast. I listen to a lot of podcasts. This is where my culture comes from. And they were discussing understanding of things, and they asked some people, do you understand how a bike works? Can you explain how a bike works? And people are, I understand how a bike works. And then they start explaining, and then pretty soon they understand that they don't understand. You don't really understand how a bike works. You can, if you're given the separate pieces, you would be unable to reconstruct your bike. Most of the people don't really know where the several pieces go, and even very good professional bikers, they know the pieces that break many times, but they don't know the solid pieces so well. So this is to say that if you want to be able to reassemble your bike a little better, you should give direct proofs. And right, so I want you to compare with this result here with the following conjecture, which is Valè's conjecture. Which is that if you have gamma, a co-compact lattice in SLNR, or SLNQP, or in fact CAD0 space, then you're going to take the regular representation, and you look at the sum gamma in a ball of radius r. So now, the ball of radius r is in your co-compact lattice. And you're going to sum all the coefficients. So now it's the regular representation. And you want this. Okay, then there exists d greater or equal to 0, and so that this is less than or equal to a constant that depends on V and W times R to the power D. So each time you take so that's for any V W in L2 of gamma, there exists a constant VW that depends on R, such that the coefficients, when you sum the coefficient of the regular representation of a ball of radius R, this is a polynomial. This behaves like a polynomial.
Can you repeat like the order of the quantifiers? Like
All right, yeah, let me just put the order of the quantifier better. So you take your lattice. So for any pair vector, you have a constant. So that the coefficients of the regular representation, sum over a ball of radius R, behave polynomially. The polynomial is fixed once and for all. They behave polynomially in terms of the size of the ball, in terms of the length.
so capital D only depends on.
Yeah. The group, yeah. So okay.
So that comes first. So there exists a
Yeah.
subset for all.
Yeah. There exists D greater or equal to 0, such that for any vector, you can find a constant that's going to adjust the. That's going to adjust the. So basically, you have a number, and when you sum the coefficient of the regular representation over a ball, you behave like a polynomial in this ball.
Where does X appear in the statement?
So either gamma is a co-compact lattice in SL and R, or a co-compact lattice in SL and Q, or a co-compact subgroup in a CAD0. It's a conjecture. So.
Okay, I see.
And conjecture is true for rank 1, anything that's vaguely rank 1 in a sense. And it's true for SL3QP, SL3R, SL3C. So this is Ramager, Robuchon, Steger. This is Vincent Laforgue. And in my PhD, I extended that to E6 minus 26, which is a Lie group nobody gives a shit about. So that, yeah, and my other advisor in Zurich always thought I was a loser for not solving this conjecture, but now it's been 20 years in holding, so I'm fine. Sorry?
So he also didn't solve it.
No. He tried. Okay, so right. So okay. So this is an open question, and if you look at that, you would say it's something that's tempting. Something that's tempting is to say, well, I'm going to go all the way to G, to the ambient group. Although if you have a CAD0, you don't have. But if you're in SLNR, what's tempting is to say, well, I'm going to take this thing and integrate it over a ball of radius R. So. Well, and I'm going to do it maybe with another representation that I know how to integrate with. And then I use the theorem and then I make a small false assumption, which is that there is a uniform bound on the dimension of those k finite vector. This is false. So I make this small false assumption, and I get integral of Borel radius r of this guy here squared, and then some false assumption that allow me to forget about those guys. So I'm just gonna forget about it. and then I recognize that this is the Harish-Chandra function, and I say, well, Harish-Chandra actually proved that this behaves like a polynomial. This is actually and then I'm almost done. That's not. It's a conjecture. It's open. It's open. Have fun. I can tell you more about the conjecture, and great. I can tell you more about the conjecture, and I wanted to say a few words about the proof of this theorem. So I'm going to give you just ingredients of the proof. So first a few words about this theta g, which is the Harish-Chandra function. So how do you get the Harish-Chandra function? First, you have to define theta t, which is given by some formula, 1 over 2p, integral 0 to 2 pi. It's not a very enlightening formula for me, who's very bad at integration, and definitely writing some bytes without bothering to take them apart. So this is a piece of the Harish-Chandra function, and we know, if you know how to integrate, this has asymptotics that are known. And if you take, in the case where G is SL3R, then you have A, which is a diagonal matrix, and it's diagonal T1, T2, T3 in plus with product is equal to 1. Then you define the function over TA to be this theta of T1 over T3. You kind of forget the second one. You kind of, oh yeah, you want them in A plus, so they should be ordered bigger to smaller. And right, so, and then we need something which is the Harish-Chandra spherical function. Why do I remove that? Like this. Let me just denote it. Spherical function, which is going to be the integral over k of rho of h gk inverse 1/2 decay. And what's happening here is this is a number, and so h of, so I take an element h of g, and that I write as k prime. Yeah. No, k-a-n. is just A. Yeah, it's just A. This is the function that picks the A element, that picks the flat piece. Right, so this flat piece, then this flat piece is going to act on this flat piece has an element in the Lie algebra, and it's going to act on it's going to act on your nilpotent piece, and so it's just a number. It's the determinant of A. This is a number, and the reason why I'm telling you that is that it gives you a Haar measure. A Haar measure decomposition. Which means that if you have a function, if you want to integrate a function f of g dg, you can decompose the integral with k n, and then you have f of k a n, and then you have it's just rho a d n, and then dk. So that's a Haar measure formula, which you have something complicated and you decompose, and it's quite miraculous. I think it's quite miraculous because if I were naive and I say, oh, it's KAK, there's a compact piece, there is a flat piece and another compact piece, the whole thing is flat. But no, it's not. The compact piece is going to mix up everything. All right, so, not very long time, 3 minutes remaining. In the 3 minutes remaining, so there is an intermediate step, which is the following proposition, and it's if you take G is SLNR, and now you take n greater or equal to 2, and that could be any connected real semi-simple Lie group with finite center, and you have pi, which is weakly contained in the regular representation now. Then you can estimate that IGVW is less than or equal to your Harish-Chandra function times dkv dkw. Right, so this part is kind of a direct computation using this Haar measure decomposition formula. What you do is first you have to assume you first have to assume that so you reduce to the case where V and W are positive. So first you do the case of the regular representation. You only need to do the case of the regular representation because then the other one is going to roughly resemble, so roughly the same inequality is going to be true. And then you reduce to V and W positive and K invariant. So all you need to prove is this inequality without, you have 1 here because you're K invariant. And for that you actually write the integral as V of G inverse X W X d mu dx. So that's your Haar measure, and you integrate this thing. That's the definition of your inner product. And you're going to bound it by, where did it put? Oh yeah, and then you're not going to care about the absolute value because my vectors are positive. And so then you use the Haar measure decomposition, and you write it as K, and then AN, and then this thing. And then on AN, you're going to use Cauchy-Schwarz. You're going to use Cauchy-Schwarz, and then reassemble your thing smartly to get the norm of V, the norm of W. And while you're doing that, you're doing some. You're actually no. Actually, you should do it like this. Which W G inverse X GX. You make some change of variable, and while you reassemble your thing, you get some kind of change of variable which make your Haier-Strender function pop out. And then you'll end up with integral over K of your thing, and then you recognize your Haier-Strender function. That's the 3 minutes. That's the 3-minute thing, and then there's one part that you have to accept. Well, or accept, or it's a more standard piece. It's a bit of an ersatz of the relative property T for SL2R semi-direct product, and if you have a finite dimensional representation of SL2R, no invariant vector, and you have P representation, a unitary representation of the semi-direct product of G acting on SL2R acting on V, no invariant vector, no V invariant vector. Then if you restrict it to G, just to this part acting, it's going to be looking like the infinitely many copies of the regular representation. And then to get the full proof of the Oh theorem, then what do? You have to look at the. So I do it for SL3R. It's G. You're going to look at G, which is the semi-direct product of V with S in G, and S is SL2R. That is in SL3, but like this. And then it's computation again, same type of computation. You take your element, you decompose it. Now you're going to decompose it in. You're going to look at B, which is A intersect S. So the diagonal matrices, which has 1 here, and then you have C, which is the diagonal matrices, which have same thing here and another element here. So they're going to commute with this S, and so you can decompose your G well enough so that when you do your computation, you're going to be able to use that and play it. It's a hand-wavy proof of the Hee Oh and Benoit's thing. It's relatively well done in Yves Benoit's notes. You can read. I mean, I could read it. So and so I was slightly so it's slightly disappointed because it seems that you don't really get away of the relative property T thing. And the relative property T for SL2R semi-direct product with R2. So yeah, it's a mysterious fine analytical point. which I was always happy to accept it as a bike and ride it. But it's right. So it uses kind of heavy machinery, but it's not that disturbing once you can translate it into the fact that so I did put it as an exercise where you have to accept a bunch of things, but the exercise kind of goes like this. So you look at SL2R acting on R2, and then you do some Fourier transform on R2, and you have an almost invariant vector. You translate that into measure on your R2 piece, and then you take your limit because you have almost invariant vector. In the limit, you're going to find your measure, which has to then do SL2R invariant. And the SL2R invariant, there's no SL2R invariant measure on R2 except for the Dirac mass at the identity. It's kind of believable because SL2R acting on R2 is going to take sets and deform it. If you have some eigenvalue which is not 1, you're going to smash stuff in one direction and stretch stuff in the other direction. So you can't have an invariant measure that's allowing you to do that. So the only invariant measure is the one at the 0 because you don't do anything in 0. And then you have to translate that invariant measure back into invariant vector. And that translation is the finite analytic point, but you know, it makes sense that it has an invariant measure. And once you have relative property T for SL2R symmetric product with R2, you have, so relative property T tells you that if you have an almost invariant vector by the big thing, you have an invariant vector by this R2. And your invariant vector in R2, this is fun computation with matrices. You just move it around everywhere. And this is what SL3R does. You take an element, if you take a matrix which has ones everywhere and a non-zero element somewhere, you conjugate it, it's going to go everywhere. And those are fun computation that are interesting to do, like matrix computation, and you very well see that if you conjugate stuff, you can do wild things just by conjugate a few matrices in SLR. And I'm going to stop here. Thank you very much. Sorry. Whoa.